And we'll move right ahead. So next up, we have Dr. Ramin Ayanzadeh, who will be telling us about their work on optimizing QAOA algorithms. Dr. Ramin is a CI Fellows postdoc at Georgia Tech, where he works with Professor Moinuddin Qureshi, otherwise known as Moin. He has previously finished his PhD at the University of Maryland, Baltimore County. His current research focus is on systems and architectures of quantum computers. He currently is on the job market. And today, again, he'll be presenting his work on quantum approximate optimization algorithms. So I will let him take it away then.
Good afternoon, everyone. This is Ramin from Georgia Tech, and I work with Professor Qureshi. Today, I will be talking about FrozenQubits that improves the fidelity of QAOA applications via removing hubs or hotspots. We already had a good introduction about quantum computing, so I'm not going to spend too much time on that. Quantum computers can answer questions that are beyond the capabilities of classical computing. Quantum hardware are noisy, but unfortunately, near-term quantum computers cannot afford the overhead imposed by error correction techniques. We are in NISQ era where we are interested in performing computations in the presence of noise, and error mitigation is the main venue for achieving goals. In this talk, we are going to talk about optimization, which is one of the candidates for demonstrating the supremacy of quantum computers in near term compared to the classical algorithms. QAOA or quantum approximation optimization algorithm is the leading candidate for demonstrating the supremacy of quantum computing in near term. And the goal of QAOA is to find the global minimum of this objective function, which is NP hard. Let's take maxcut as an example. To solve a maxcut using QAOA, we need to first design a circuit. QAOA circuits are multi-layer, and in each layer of the circuit, we translate every edge of the problem into 2 C0 and 1 RZ rotation. And then the rotation values are optimized using the outer loop classical optimizer. And I would like to highlight that every edge is represented with 2 C0 because we are going to leverage this knowledge for introducing our technique. To demonstrate the supremacy of quantum computers using QAOA, we need to tackle problems that have some hundreds of nodes, and we need to repeat the circuit for at least 12 layers. If we want to calculate to know how many CNOS we will need, depending on the topology of the underlying problem graph, we will need to run circuits with thousands and even millions of CNOS reliably. And this problem is magnified when we compile our circuits into NISQ devices that are sparsely connected. Here, we can see the connectivity map of IBM Montreal, which has 27 qubits. For example, if we want to apply CNOT between qubit 2 and 4, they are not physically adjacent, so we need to apply a swap operation. It is possible to resemble a fully connected device using swap operations, but swaps are costly. Every swap is represented with 3 CNOTs. So this chart shows the number of CNOTs before and after compiling to a grid device. As you can see, the number of CNOTs before compiling grows linearly, but after compilation, the number of CNOTs grows super polynomially. CNOTs are noisy. On average, these days, every CNOT operation has the error rate of about 2%. So we are limited to reliably running circuits with few tens of qubits, while we need to run QAOA circuits with thousands or millions of circuits. So as a wrap up here, we can conclude that the difficulty of optimization problems in classical computing primarily depends on the number of nodes. However, the fidelity of QAOA applications primarily depends on the number of edges. But we observed that not all nodes contribute equally to the circuit noise. This chart shows the airport connection in the United States. As we can see, there are some hubs or hotspots, such as New York, Chicago, or Atlanta airport, that have more than 10x higher number of connections compared to the average number of airport connections. But this observation is not limited to airport traffic graph. In fact, most real-world problems have a power law graph representation where we have a few hubs or hotspots that have a significantly higher degree, and there are many, many nodes with lower degree. If we can find a way to get rid of these hubs or hotspots, we can significantly drop the edges that are connected to those hubs, and the underlying circuits can be run much more reliably. There are some circuit cutting techniques that tries to partition the circuits by cutting the wires, but however, these techniques unfortunately are not applicable because at the presence of hubs or hotspots, it is non-trivial to partition circuits into smaller subcircuits. To this end, we propose FrozenQubits that escapes hotspots without compromising the quality of solutions. Excuse me. FrozenQubits identifies hubs or hotspots, and then substitute that hub with its two possibilities, +1 or -1. So from a higher level perspective, FrozenQubits is a divide and conquer approach. Why we substitute the values +1 or 1? So because after the measurement, we will find the value of every qubit either +1 or -1. So if we substitute the specified hotspot qubit with +1, we will go to half of the search space that we have. If you substitute with -1, we will go to the other half of the search space. So with substituting these hubs with their two possibilities, we can partition the search space of the problem into smaller problems. However, with every hub reduction, we significantly reduce the number of edges that are connected to those hubs. I would need to highlight that the number of qubits that we eliminate in FrozenQubits does not scale with problem size. In fact, we only need to freeze a few hubs or hotspots, and increasing the number of hubs, we have observed that does not help. Compiling circuits is non-trivial, and it can take many hours, if not days. So if we are partitioning the search space into smaller subproblems, then compiling all those subcircuits can be a bottleneck for our design proposal. But when we take a closer look at the circuits for all those subproblems, we observe that in terms of the structure of circuits, all those subcircuits are identical, and they only differ in rotation values. So we don't need to compile all those circuits separately. We can compile only one template circuit, and then after the compilation, we can edit the rotation values to form the executables of all those subproblems. So in FrozenQubits, we only compile one circuit, which is simpler because we are removing the hubs or hotspots. In the same way, we don't need to run all those subproblems. On the left side, we have an example that we partition the original problem into two subproblems, and on the right side, we see their landscape. As you can see, if you choose any row in any of these subspaces and flip all values, you will find another row on the other subspace whose objective values are identical. In fact, the entire landscape for this problem is symmetric. And this is not limited to just this example. And we demonstrated in our paper that if all linear coefficients are 0, the landscape of the problem is symmetric. So we only need to solve one of these subproblems and then infer the output of the other subproblem by simply flipping all bits in the output distribution. This helped us to significantly reduce the number of circuits that we needed to train in our model. To evaluate the performance of our model, we use Barabasi-Albert algorithm for generating random power law graphs, and we use approximation ratio gap as our figure of merit. This chart shows the approximation ratio gap of the baseline, which is the standard QAOA, and compare it with FrozenQubits when we freeze only 1 or 2 qubits. As we can see, FrozenQubits significantly reduce the rate which approximation ratio gap is increased when we increase or scale the problem sizes. And we observed that on different IBM devices, we observe up to 57 times fidelity improvement when we freeze only 2 qubits. To see why this happens, we can go more details and see the number of CNOTs and depths of the circuits. The top chart here shows the number of CNOTs when we freeze 1 or 2 qubits, and the bottom chart shows the depths of the circuit when we freeze 1 or 2 qubits. We see that freezing these two hubs significantly reduces the number of CNOTs and depths of the circuits that are directly connected to the noise of the underlying circuit and the decoherence of the circuits. But running on near-term or existing devices is not enough. To demonstrate the supremacy of quantum computing using QAOA, we need to tackle problems at scale. So we studied the impact of FrozenQubits when we wanted to tackle a 500-node problem graph. This chart shows the number of CNOTs for a 500-node graph when we compile it to a 50 by 50 grid connectivity hypothetical quantum computer. We see that freezing qubits significantly reduces number of CNOTs, and more interestingly, we observed that more than 90% of these CNOT reductions are due to the reduced number of swaps. And we don't have such large-scale devices yet to compute the achieved fidelity improvements. So we use a simple error model, and we use 0.1% error for CNOTs and 0.5 redot error and 500 milliseconds as the coherence time of qubits. And we observe that freezing up to 10 nodes can provide up to 2 orders of magnitude improvement in the probability of success of running such circuits. And finally, we take a look at the compiling time. As we can see, since we only compile one circuit, and the sub-problems get smaller when we remove the hubs or hotspots, we observe that FrozenQubits, the compile time in FrozenQubits is significantly less than the standard QAOA. And indeed, the amount of time that we save in the compilation phase is much more than the entire pre-processing, post-processing times that FrozenQubits impose. And we hope that FrozenQubits can expedite the achievement of quantum advantage in near term. To wrap up, QAOA is the leading candidate for demonstrating quantum advantage in NISQ era. The fidelity of QAOA primarily depends on the number of edges, and we observe that most real-world problems have a power law distribution. We leverage this observation and propose FrozenQubits that eliminates these hubs or hotspots without compromising the quality of solutions. And using IBM devices, we were able to achieve up to 57 times improvement in the application fidelity of QAOA circuits. Thank you, and I'm happy to take your questions.